học gắn vô tên tên hash ra thích này làm sao còn chất là
Okay, so just to make up this, we are not going to show you examples of applied mathematical induction, but these are the statements of stating the mathematical induction, why we can prove certain things in slightly different form. A lot of times we have a statement like P, and depends on X or N. A lot of times we use N. So we have a statement like this: for every n in greater than or equal to a threshold A, we want to prove that P of n is true. So actually, your teacher or your textbook will say, well, prove the basis, which is P of A, and you prove the induction step. Right? So for all n greater than or equal to A, if you assume that P of n is true, you try to prove that P of n plus 1 is true. So certainly, the thing it works here in this domain here is not just numerical. It has to be so-called discrete, like you can say first, second, third, fourth, and so on. So that is, this domain is discrete. We are not trying to say what discrete means. Turn out discrete is a technical term in mathematics. But intuitively, that means we can say first, second, third, fourth, fifth, and so on. So if you have a discrete domain, then you on one hand you will say, I want to prove that for all n greater than or equal to a threshold, P of n is true. Then the mathematical induction is that, well, I can tell you that this statement, this quantified statement, universally quantified statement, is equivalent to this quantified statement, like conjunction of P of A and this universally quantified statement. So instead of proving that, you prove this, then your job is done. This is called weak form. So the weak form, usually you say, the textbook will say this is a basis, so-called the basis step. And this is so-called the induction step. Right? Okay? And you prove the basis, P of A is true, because this is n, right? And then you prove the induction step. In the induction step, you have a sort of a slightly better deal. Is that you still deal with universally quantifier just like this. You're not going to escape from this universally quantification. However, in the induction step is that seems that you have something that you can rely on in your pocket, the hypothesis, which is you may assume that P of n is true. So this is in the textbook, you will see that this is so-called the induction hypothesis, right? So the textbook will write that assume P of n is true, right? Assume that P of n is true, and then you prove P of n plus 1. Now apparently this is easier because you have this sort of free lunch. The free lunch is that you assume that P of n is true. Over here, you prove that the statement is absolutely true without help, apparently. Right? This is absolutely true. You prove that for all n greater than or equal to 3, n squared plus n minus 4 is divisible by 5, something like that. You prove a statement that is absolutely true in its own miracle. This is different. You prove the basis, which is the handle that n equal to a. You prove the induction step is, okay, this is universally quantified, just like that. But you have a free lunch that you can say, assume P of n is true. You assume that for this arbitrary chosen n greater than or equal to a, n squared minus 4n plus 5 is divisible by something. So you assume that, and then you proceed with say, can I prove P of n plus 1 to be true? So you have these things in your pocket, you may assume. So that is sort of the extra thing that you can deal with. Okay? We call this weak form because there is sort of a slightly better statement that you can prove. This turn out all these are equivalent in terms of logic. You can prove the basis, and you can prove the induction step. However, in the induction step, you have an hypothesis or hypotheses that is not just P of A is true. You have P of A, you have P of A plus 1 because it says n. You may assume the entire thing to be true. That means every single one is true. And these are free lunges. So you can use P of A because it's true. You may assume P of A plus 1. You may assume P of n. You may assume P of n minus 1. You may assume the P of n over 2. If n over 2 makes sense to us. Because n may not be, you have no control what n is, right? N may be even or odd. So n over 2 may not make sense. But if it makes sense, if you say, okay, P, for example, you may say, okay, what about P of n over 2, the floor? Like, floor meaning that you throw away the fraction, right? Okay. So you may assume that and you happen to be here. Maybe yes, maybe no. Be careful. Because this starts from A, and you don't know what A is. How do you know that A and n, this boundary, will capture n over 2? Maybe not. Think about this. So if you have A, this is A, and this is n, right? N over 2, where it is? It's not always here. It's not here. It may be here. Because A may be a billion. Right? So n over 2 may be somewhere here. You have no idea what n is. N is anything greater than equal to A. N may happen to be 10 to the power 10, let's say. Right? In that case, n over 2 is somewhere here. But it may be this, right? Or something like that. I want to say what? So that means you may have more hypotheses, but the burden is to make sure that whatever you use as a hypothesis, this guy here, this index, is not out of range. Okay? If it's out of range, it's not part of the assumption, and don't use it. So this is a very common mistake for beginners, because they just think that, oh, I can assume all of this. So what about P of n over 2? Even the floor, right? Well, it may not be within here. And if it's not within here, then you don't have that in your assumption. You have to establish that. Okay? So, and then with all this help, you prove P of n plus 1, right? Okay? So that is the deal. We call this strong form because apparently this is stronger than this. So why not using this? So you will see that in most textbooks, once they introduce a strong form, most authors will just assume that the mathematical induction is written in strong form because it is just a more general way to use induction. Okay? So they don't say strong form. They just say by induction or use mathematical induction on n. Now, most of the time, it's a good habit to say when you say induction on something, you don't just say by induction. That's a bad writing. It's just like if I come to this room and I say, oh, let's count something. Let's count. I'm sure that most of you will scratch your head. Count what? I mean, you ask me count what? What do you want me to count today? So I have to say count the number of bottles on the table, or count the number of pencils used in this room. So I have to give you a handle. So when you say induction on what? Of course, when you have this simple example, like in all the textbook, is to prove this, right? Then the only way to deal with it is to do an induction on n. But suppose you have a statement, say n to the n minus m to the n is da 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 da, right? You have such statement. then, so this is true for all n or m greater than equal to 4 or n greater than equal to 5, something like this. You try to prove this. So induction on n, or induction on m, or induction on n plus m, or induction on n minus m, which one are you talking about? So you have to know exactly what you want. So, it's a training. So you don't just learn from example to say, yeah, the example will say by induction. Like a better writer would say by induction on what? Okay, even as simple as this. But you start the training, say induction on n, induction on what? And then you lead the reader know your intention. Okay? So presenting a proof, presenting an argument, of course you may want to get it right. But at the same time you want to interest the reader. You don't want to say the reader will say, what are you writing? Throw it away. Because it doesn't make sense. It's difficult to read. So you want to have someone to appreciate your writing. Right? Even you go to work in a bank, work as a programmer, or work in an industry. When you present something, you want someone to appreciate what you do, what you have done. So you have to be articulate, right? You learn to be articulate, but you learn something not overnight. You have to start learning the things at a young age, at the beginning, and practice and practice and practice. Okay? So on one hand, I try to teach you, okay, this is the right thing, this is the right logical reason. On the other hand, hopefully, you know that whatever you write, whatever you try to convey, you want to make it clear, just as a habit. Not always multiple choice. It's always presentable. You want to convey, you want to tell the reader what you're trying to say. You try to just like to write a good story. You lead the reader into the scripts of your story. Okay? Okay, so now we go to regularity. Okay? So like I said, this is the big topics. It takes about 3 to 4 days, 3.5 days. Okay? So first, all the topics involve languages. The entire course is about formal languages. But languages study in different aspects, with different kinds of models. So first we want to ask this common question. What is a language? And we say language is a collection of strings. And then you could ask what is a string? And then so turn out these concepts we borrow from sequences. So, first we learn so-called strings and languages before we really look at machine. Okay, so what is a string? So first we have an alphabet. What is an alphabet? Just like the English, they have A, B, C, D, E, lowercase, uppercase. And I don't know about your language, Vietnamese. Do you have you must have an alphabet, right? How many characters in the alphabet? Huh? 29 with accent. So I'm sure that you have something like this, right? So then, is this enough? Is E is an alphabet letter? Then what about this then? It says different alphabet. So you're more than 29 then. So anyway, so now we have, usually in this course we use Sigma. Sigma is an alphabet. So in an abstract way, basically this is sort of a finite non-empty set, or non-empty finite set, okay? And the kind of things inside the set is they are symbols, like A, B, C, D, E, or digits 0, 1, 2, 3, 4, 9. So this is very subjective, right? So depending on the context, suppose we are using programming language for some programming languages, say that the keyword, the reserved word begin is a token. So a token is a single symbol, right? We don't separate them. We don't separate B-E-G-I-N. So the entire thing is treated as a single symbol. So here we just say alphabet is a collection of symbols, and this collection is non-empty, is finite. We don't talk about infinite alphabet in this course. Okay, and then what will be a string? A string over sigma. So a string over a given alphabet basically is a finite sequence of symbols of sigma. So you pick a bunch of symbols and sequence. Sequence meaning that the ordering is important, right? So suppose sigma is like ABC, the tripleton, so it's ABC, A, B, and C, three symbols. So now this is a string. So B, B, C, A. Right? B, B, C, A. B is the first symbol. First symbol of the string. B is the second symbol is also B, and so on. Well, a lot of time we are lazy. This is just like the sequences you learn in algebra or calculus. So we are lazy, we just say get rid of the separators, commas, and get rid of the open and close parentheses. So we just concatenate them together. So this is a string. Okay? So it is finite. Certainly you may say, can I have infinite string? Generally you could, just like infinite sequence. But for this course, if we say this is a string, that means somehow you know that there's only a finite number of symbols. It may be beyond what you have in mind, but nonetheless, it must be finite in length. Okay, so this is a finite sequence of symbols. Well, then, certainly we allow ourselves to say, well, could it happen that we have empty sequence, right? Empty sequence. That means we have nothing. So how do we represent empty sequence like this? Nothing inside. Okay, but we use a meta symbol. A meta symbol is depending on the textbook. A lot of times we use epsilon, sometimes we use lambda. So some textbooks use epsilon, some textbooks use lambda, about half and half. So when you see this symbol, epsilon, that means the author or me is saying this is the empty sequence. Or when I use lambda, then this is the empty sequence. This empty sequence is empty, no symbol at all. Okay, so that's the simple definition of sequences. So just like whenever we say about equivalence, we can talk about equality of strings, right? So what would be two strings are equal? So equality. So if I have strings, right? So same sigma, right? So string say x1 and x2, right? So this would be string x1 over sigma. So what do you say that x1 is x2, right? Two strings are equal. So we go back to the definition of sequences. Two sequences are equal, meaning that position by position, they must be the same, right? So this equal as sequences, right? So I assume that in calculus, in algebra, you know when we say two sequences are equal, meaning that you go through the index, right? They must have the same index range, and then for each index, the position, you must have the same letter, same symbol. Okay, so this will be equality of strings. Okay, and we use this again, this notation right now. It's called sigma star. Now, turn out there's really a meaning for this star. But at the moment, we just take this as a compound symbol. Sigma star as a single symbol called sigma star. Sigma star, as of now, is the set of all possible strings over sigma. Okay, so sigma size is kind of the universe. Right, so for example, if I have sigma, which is ABC, the tripleton ABC, so think about what sigma star look like. So I can say, yeah, this is sigma star. How big sigma star is? Infinite. Why? Yes, every string is finite, it's a finite sequence. But I cannot really control the length for each string, right? So when you say, okay, what about, I have 10 letters. I can say, well, what about 11? What about 25? What about 220 billion? So in a sense that you could have epsilon here, or it's right in the middle, and then you could A, you could have B, you could have C, you could have AA, you could have BA, you could have BBB, you could have CCCCA, you could have AABBCCAA, right? You could have that, and so on. Now, certainly you may say this is chaotic. Maybe we should not view sigma star like this. Your friends who may see universe slightly different from the way we do. So you may see that sigma star somehow is organized in this way, epsilon here, A here, B here, C here. And then AA here, AB here, AC here, BA here, BB here, BC here, and CA here, CB here, CC here. Right, so you know that this guy, enumerating the members in sigma star in specific way. Okay? So actually there's some kind of length concept underneath this guy's mind. So he is enumerating the members by sort of inducting on the length of the string. Right? Length 0, length 1, length 2, length 3, length 4. So this is chaotic. Okay, so now we want to see what can we play on strings. One is the length, right? So sort of with functions or operations on strings, right? So the first one is the length function. So what kind of symbol we use for length function? Length. We overload ourselves. We use absolute value sum. Different textbooks would have different notation, but we use this absolute value. Okay, so it's not really absolute value, but it's these two vertical strokes that indicate this is the length of a string. So what is the domain of this? As you give me a string, I give you a natural number. So the domain of this function is sigma star, right? Because we want to say the length of a string. So this is the domain. And the length is to count the number of the length of the sequence. So it's going to be a natural number, right? Remember I introduced this? Natural number, this is the set of all naturals. You start with 0, right, and so on. So actually, so for all x in sigma star, so for all string in sigma star, so we want to say the length of x, right? So this is the length of x. We are going to use our method reasoning. Is the length of the sequence denoted the sequence of x, right? So we just assume that x is a string. So x is a sequence of is a finite sequence of symbols. So it makes sense to talk about the length of a sequence because in algebra, in calculus, when you learn sequences, you know the length of a sequence is to count the number of symbols starting from the first one to the last one, right? So that is the length of a sequence. And assuming that we have that idea, not known here, but it's very easy to understand, and that length is the length of our string. Okay? Now, I'm sure that in programming, you implement length function. like if you do programming, computer science 1, 2, or data structures somewhere, then you will say, I am going to implement the length function for the list, or the size function for the list. So somehow you cannot say, check the calculus textbook, check the algebra textbook. You have to write the function yourself. So now you use an iterator, or you use some kind of loop to say, I go through the loop, I go through the elements one after one, or nodes one after one. Or better yet, you may say, I'm going to use recursion. I'm going to write a recursive function to compute the length. So what I want to do is that, well, we learn induction, assuming that we erase that, but the induction concept works here. So can we define the length formally using induction so that we can implement the length function with the recursion following the inductive definition? So how do we define this inductively? Okay, so this is what we do, right? So we so I can do this, right? So so for arbitrary x in sigma star, right? So we want to say what is x, right? So the induction is this induction here is on conceptually on the length of the sequence, right? Conceptually. So we will say, yes, if x is empty, what would be your length function that you kick out? 0, right? Nothing. On the other hand, if x is longer than this, right? So kind of like, okay, if this is x and x is completely empty, nothing, so I kick back, the black box will kick back 0. But if x is not empty, so the way we force ourselves, or the implementation, or the recursion, or the induction, forced upon us is to say, if it is not empty, then this sequence of symbol, isn't it? It must look like this, right? If this is not empty, it must look like this A1, A2, da, 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 da. And this is AN, and this is AN plus 1. Right? You must have x in this form that you have, you look like this, A1, A2, da, 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 AN, for some n greater than or equal to 0, right? You must have that. Because your length, if the length is 0, then nothing. But if it's not empty, then you must have sort of the last guy, the last element that I can isolate. So n cannot be 0. This cannot be 0. That means you must have at least 1. So I just call this, I just use some fancy notation, this is n greater than or equal to 0. So actually, if x is of the form, right? So y followed by, say, a, for some a in sigma. So in other words, I can view this x as a sequence, says y, and then followed by this a. Right now, a little bit tricky. So this is a sequence, right? So for some y in sigma star and some a in sigma, right? So you may, if you are really clear-minded, then you will say y is a sequence. So turn out it may look like this, right? Right, because this is a sequence. Well, let's don't argue with that, because in order to avoid this, then I have to introduce a concatenation first. And I don't want to introduce a concatenation before we talk about the length, because it's a very naive concept. So So actually, you can view x is sort of like, okay, you have a prefix and followed by a last symbol. So basically, the black box is going to kick back the length of this shorter one, the prefix, and plus the contribution from A, which is 1. Right? And of course, just like your understanding of recursion, I assume that some of you done recursion programming before. So you may say, well, then what is y? What is the length of y? What is the length of this guy here, or this? Well, then you ask yourself, go back to the recursion. Is y empty? If y is empty, then this becomes 0, because you go to the basis. If y is not empty, then y is going to be decomposed into some prefix followed by another symbol. And then you have the add 1 effect. And then you have this black box making the recursive calls here. Okay? So that is the kind of sort of recursion that we deal with. Okay? So a lot of times, we use this in our implementation without really knowing the semantics of this. This depends on our sort of high-level understanding of the length of sequence. We count the numbers. So this helps us tremendously because we can capture this picture and reason this with our high-order understanding. This one, if we don't have any explanation, and if this induction is kind of sort of complex, then we have no idea what the recursion, when we unscroll this recursion, what are we dealing with? Okay, so one is syntactically correct. One is you got to help yourself to understand what this is about. Okay, all right. This itself may not give us a good implementation. This is the level that we can use recursion to help and to argue the correctness of the function, the properties. Okay, so this is the operation. Right. The second one is the concatenation. Okay, so what is concatenation? Okay, so the concatenation is this. Concatenate two strings together. So that means concatenate two sequences together with the given order. So concatenation, at the beginning we use this little circle, a binary in-place operators. So it would take a string, and then you would take another string. So the domain is the order set, sigma star cross sigma star. That means we pick two arbitrary strings, each of them from sigma star, a typical string in over sigma. And then what we return is sigma star, a sort of a concatenating string. So how do we define this? So for all x1, x2 in sigma star, right? So here, and here. So what is x1 circle x2? So this is the concatenation of x1 and x2 in a given order, right? So the first is x1 and then x2. So what is a concatenation of x1 and followed by x2? Very natural. The sequence of concatenating x1 sequence and x2 sequence. So what is this? So this is the string whose sequence, right, is the concatenation of the two sequences of x1 and x2 in a given order, right? So basically, we are cheating. We use our understanding of sequences in algebra or calculus, so this very simple, straightforward understanding to use it for string. Okay, so again, can we define concatenation using recursion, using induction? And the answer is yes. So how do we define this concatenation inductively. So this time, life is not so obvious. Because over there, when we define the recursion induction on, say, for this length function for a given string, you may say, well, what other choice? There's only one string. So the induction must be on the string, must be on the sort of the numbers, the length of the sequence of the string x. No choice. But now we have a binary operator, binary function here. So x1, x2, and what will be the induction on x1 or on x2? On the length of x1 or the length of x2? So, turn out there are choices. And you can try the choices. So one of them turns out to be more natural than the other. The natural one is the induction is on the length of x2 rather than the length of x1. So we want to say that this is on the length of the second operand. So that means, with that in mind, so for all x1 and x2 in sigma star, how do we define x1 circle x2, the concatenation? So we want to say, look, the induction is on this guy, on the length of this guy, from small to longer. Okay, so we say the basis is that when x2 is empty, basically they say the length is 0 now. The length of the second operand. The length is 0, the smallest one, right? So that means I'm looking at x1 circle epsilon. Remember, this is a definition. Obviously, we can define whatever you want. But we want to make sure that this definition coincides with what we have in mind here, the semantics. Certainly, when we have two sequences, one sequence is here, then the second sequence is empty. When we concatenate these two sequences in our common sense, then the kickback is just the fourth sequence. The second sequence is void. So our definition is to say that, okay, just kick back x1. Right? Natural. Because this is going to coincide with what we want to say. Well, what if this is x2 is a little bit longer? So longer now, we want to say that means what? That means x2 is written in the form of like y followed by a, right? So like this. The sequence y followed by this symbol a. So x2 is going to be for some y in sigma star and a in sigma. You must be able to spot that because x2 is not empty. If x2 is empty, this is our basis and you return already. So the x2 is a bit longer than empty. That means we force ourselves to view the x2 sequence in prefix and a last letter, last symbol, just like that. So I say x2. If x2 is not empty, right? So you may say otherwise. That means x2 is the form y followed by a, y concatenated with a, for some y as a string, and a is a symbol. So now you think about this. You have this x1 concatenated with this y, concatenated with a. Now this is a meta symbol. We don't really have open and close parentheses as part of the string. So this meta symbol, just to make clear between you and me, right? So this is my x2, concatenating x1. So now, what will be the black box, your function that is going to kick back in your program? So your program is to say, well, this is a longer string, but I force myself to recognize this as a shorter string prefix followed by a symbol. So I'm going to call the black box, your function, on x1 with this shorter string, and then whatever this comes back, I concatenate with a. So actually, it's going to be like this, x1 concatenated with y. So you force yourself to say, this is going to be x1 concatenated with y, and then followed by a. And it makes sense. Because when you learn recursion or induction, you know that if your recursion or induction implementation is correct, then you always fall into one of the bases. As you trace this, you will see that the second operand is getting shorter and shorter and shorter by 1. Because that's the way you force yourself. You either go to the extreme that it is 0, the second operand is, the length is 0, and that's it. Or you're going to shorten this by 1. And then you call the recursion on a shorter second operand, and that is perfect. Right? So if you unscrew all this recursion, actually you are doing this concatenation x1 with the first letter, first symbol, and then second symbol, third symbol, fourth symbol, and then the last symbol in reverse order. Okay? So this is how it is done. Okay? Some of you, if you don't take any other computer science courses, you may say, yeah, this is an overkill, because you probably never deal with recursion or induction for the rest of your life. That's okay. But if one day you say, okay, I may take a data structures, I may take a continuation of certain computer science courses. Recursion or induction are basically computer science. So if you want to have a good understanding about computer science programming, you should have a good grip on recursion. Before the birth of computer science, like in the 60s, there wasn't any computer science degree. Nothing. There wasn't any computer science textbook. So what we have people, we have very good scientists whose interests or develop computer science. So where did they get the degree? What subject matter they got the degree? It's called recursive function theory. Right. So recursive function is a synonym to computer science, to algorithm. So you will see that computer science is just like algorithm. Algorithm is just like recursive function. So in other words, if you want to have a good understanding about programming, you should train yourself to think recursively. If you can think recursively, then you overcome a lot of computer science problems. Okay? Trust me. Any data structures you have in mind, lists, trees, everything, they are recursive. You can define binary tree, you can define trees recursively. You can define lists recursively. You can implement all the functions recursively. So, recursive thinking is a key to a higher level of understanding about programming. So it's a good thing if computer science is something that you are interested in. Okay? Okay. So concatenation, we can define it recursively. And of course, we can rewrite this a little bit, the link function, because we did not have sort of the concatenation idea here. But now with the concatenation, we can express something like this better. Okay? A lot of time we are lazy. We don't want to write the little circle here in the middle. So sometimes when the context is clear, right? So this x circle y, right? So we just write this as xy. So this guy here goes away when the context is clear. Okay? Sometimes we want to emphasize that, yeah, we are concatenating two strings. But sometimes that's not really significant. We just say, yeah, put them together. So we just write xy. Okay? So that is the second operations. Okay? And then now, there's one more we are going to introduce. And then we look at some simple property, very simple. The third one is so-called reversal. Right? Reversal is that, depending on the textbook, we use this superscript R or big R. So you give me a string, I'm going to give you a string back. So for all x in sigma star, okay, so we're going to say, well, what is x reversal? Again, we're going to look at the definition, the semantics, using sequence. And then we're going to define this inductively. So xr is the reversal, is the string whose sequence is the reversal of the sequence of x, right? So now you can see that we can define this inductively. So this one is on the length of the operand, right? Okay, so how do we define it? So x reversal, and so for all x in sigma star. So again, the basis is that when x is empty. So what is the empty reversal? You have a sequence, and then you want to look at the reversal. And according to the semantics, it is the string whose sequence is the reversal of the empty sequence. But the reversal of the empty sequence in our common sense is that it has nothing. It has nothing, so that means it's empty. Right? So our natural definition is to say yes, that it's going to be empty. The empty string. Right? Okay? But if x is longer, so now we learned that the trick. So if x is longer, so otherwise, right? So x is the form, say y concatenated with a. For some, y is a string, and a, the very last symbol, must be there. Because it is not empty. It is longer than 1. I mean, it's at least 1, the length. So the a is in sigma. We're going to force ourselves to recognize that. So in this case, we are looking at the YA reversal. So what will be our natural definition to say we are going to end up with a string whose sequence is the reversal of this sequence? Well, if you have a sequence that starts with the sequence of y followed by a, when the semantic is to say to reverse this, right? So actually, the definition is the a concatenate with, so if I force ourselves to say, make sure this concatenation, the a concatenating with y reversal. So this reversal applies to y, not to a. So a, and then followed by this concatenation, say y reversal. Okay, so that is the inductive definition. Now, so let's look at some examples and some properties. Right, some example. So, for example, say you may say, what is a say BB, say BBA concatenated with AB, right? So we have two strings. So BBA concatenated with say BA. So sigma is just a stub with AB. Right? Now, certainly if you say, well, this, what kind of question it is? It's obviously, it's just like BBA, BA, right? So you may say, yeah, the answer is BBA, BA, right? What more can you ask? Well, let's be a little bit careful. Suppose we invoke the recursive implementation or definition. So actually, we say BBA, and then we concatenate with BA, right? Okay. So let's say the recursive definition is that we do this on induction on the length of the second operand. And then you will see that so this is recursion, inductive definition, right? So the inductive definition is that if this is not 0, the length is not 0, we're going to force ourselves to say, okay, isolate this, right? So actually, that definition is to say here, is to say it's BBA, x1, concatenate with this one, but then I force myself to recognize this is my y, and this is my A, right? Well, this happens to be A. Let's say this is B, this is C. Well, how about this? A, B, C, right? So this is going to be my Y, this is going to be my A, the choice of A here. So this is going to be concatenated with this, and then this whole thing concatenated with C eventually, right? And then I have to deal with this. So the recursive inductive definition allow me to have this followed by this single character, single letter concatenation, but I have to deal with this. So I ask myself, that what is this then? Well, this is not empty, so it is not this case yet. So I have to call on this case to say, well, what will be my Y and what will be my A? Here, right? So in this case, the recursive the implementation, this is my Y. Sorry, this is my A, and the Y here is epsilon. I isolate the last symbol. So the prefix Y is empty, right? No Y. Y is empty. And the last symbol is B. So again, the inductive definition is to say, okay, this is BBA, concatenated with empty string, whatever that is. When it kick back, it concatenates with B, and then, according to this, concatenate with C. It's a pain in the neck, but it is the right way to do it. Then now, the last, this is another call, BB x1 concatenated with x2. But x2 is empty. So now, the black box, the basis will say, oh, just return the first part. So over here, this is a basis. So this is BBA, right? Concatenate with B, concatenate with C, right? Okay. So now basically, you come back to say, okay, yes. Now you will see that basically we kick back and then just attach the A there, right? So this part concatenate with B, so this BB AB, and then concatenate with C, so this is BB AB C, right? So this is sort of the unscrolling part. Keep on making the recursive call. This is sort of the tail of the recursion, is to say, yeah, now you have this symbol. Actually, when you have this symbol, you just attach this A as the very last letter symbol to the sequence. So nobody is going to do a concatenation as mechanical as this. But if you implement a function on the computer, the computer system really do this for us. It's silly. But then the computer is not as intelligent as human. So the computer cannot do something like this. Okay? Alright, so now actually you can use the same idea to force yourself to understand this. Right? The recursion, the induction of this reversal actually is you reverse you throw this last symbol to the front, and then you reverse the prefix, and in the process you're doing it all over again. Okay, so now we have this link, concatenation, and reversal. So some simple properties. Right? So they are pretty straightforward and obvious. First one, for example, say all these strings are x1, x2, x3, or whatever in sigma star, right? Obviously, x1 concatenated with epsilon is going to be x1, is going to be epsilon concatenated with x1, right? It's just that epsilon is a neutral element with respect to concatenation, okay? it's not going to change the sequence of x1. Or say x1 concatenate with x2, and then concatenate with x3. So if we keep the string x1, x2, x3 in the order, then this concatenation is associated, just like the associativity we studied. So this is x1, x2, x3, and we do this concatenation first and then this. And turn out they are the same, right? Pretty obvious. But certainly the commut is not commutative, right? So x1 circle x2 is not equal to x2 circle x1 in general, right? So we don't have commutativity, but we do have associativity, which is pretty natural. Okay, so this will be about concatenation. We can mix things up, right? So for example, say for all x1, x2, x3, say dot 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 in sigma star. I don't know how many we involve. So let's mix up this the length function and the concatenation. So x1 concatenate with x2 and the length of this. Right? Think about this. Well, this is going to be the length of x1 plus the length of x2, right? So if we concatenate two strings together and measure the length, then isn't it true that obviously it seems that this is the length of x1 plus the length of x2. Now, intuitively it is so. But if we try to prove it using inductive definition of concatenation, I cannot remember if I put it as a homework exercise, then it is not that straightforward yet. But if you have some experience in induction proof, then it is straightforward. So you can try that and see if you can prove it, not just by saying, oh, sequences. I say use the inductive definition of concatenation and the length function to prove this. Okay. So for example, what about this? X1 reversal, the length. The reversal doesn't really change the length. It's going to be this, right? Okay. So the length sort of interplay with the concatenation and reversal. And then now also a mix. So for all x1, x2, x3, whatever, say in sigma star, if we reverse the reversal of a sequence, well, we get the same sequence back, right? So x1 reversal, and then reversal, we get x1. Right? And if we say x1, circle x2, reversal. Well, what do we have? If we concatenate x1, x2, and then take the whole thing reversal. What do you think? What will be the answer for that? You see naturally what the outcome should be? Well, reversal is to reverse a sequence of a string. So we end up with this reversal sequence. So now we have x1 followed by x2 and then reverse them. So what do we have in the outcome? Any help? Yes?
X2 reverse concatenate.
Huh?
X1 reverse.
Sorry?
X2 reverse.
Yes.
X1 reverse.
Yes. So actually, you reverse that. You reverse the block, and then you reverse each block, right? So if you reverse this structure, so it becomes X2, X1. But also you reverse the structure between X1 and X2, okay? Well, all of them, we can prove the statement using the inductive definition. And of course, you may say, well, I can see that intuitively true because we just look at the sequence, right? We just look at the sequences of x1, x2, x3, and then expand all these sequences using the elements, the symbols of x1, x2, x3. You can do that. But the whole idea is that you learn something new. Can you use this inductive definition to prove some basic properties? They are pretty straightforward and intuitive. But as intuitive, as straightforward as this, can you make a nice proof? Can you do a perfect proof, right? To test your understanding. Okay. So these are simple. And of course, we could have some very complex one. Okay, but we don't want to deal with that here. Okay, so all this will give you an idea what strings look like. Well, then the next level up is languages. Okay. So again, we have a sigma. So this is an alphabet. This is a non-empty finite set of symbols. So when we say a language over sigma, what is it? Basically, a language over sigma is a set of strings over sigma. Now, the key word here is I did not say that, the set of all strings. The set of all strings over sigma. This is the entire universe. This is sigma star. I'm just saying that this is a set of some strings over sigma. So in other words, if this is the universe sigma star, a language as simple as that is just a subset, say L, is a subset of sigma star. So that is a language. So this set actually may have nothing at all. So this is so-called an empty language, right? Nothing, no string. Or the entire universe is a language. So this is sort of the largest language you have. So it is a language, right? And somewhere in between like this is a subset. It is a language. So a language is just a collection of strings. So why do we study this? Computer science, the entire subject, is recursive function theory. When we look at recursive function, we study the properties of the function. And the properties of the function is identified with the language. Everything you work on. When the teacher say, well, this is homework number 1, exercise 1, you are going to write a program to do certain things. Actually, the requirement is this language L. So for example, your language L is, say, your teacher, instead of saying it, actually the teacher used to say, well, I want you to decide if this input X in, say, this digit, right? And that this X has certain property, right? Actually, your program is going to decide whether a string composed of digits satisfies certain properties. And if so, your program is going to say yes. If not, then the program is to say no. So actually, your program exhibits this kind of language. So everything you do in programming is about the membership. Okay? Not only that, imagine your program, submit your program to the compiler. whether it is a C compiler or a Java interpreter, your program actually is a collection of tokens. This collection of tokens may look like this, right? Your program text, right? So maybe main dot 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 dot, and then open, and then dot dot dot, right? So actually, if you look at your program, it's a sequence of tokens. It's a string. The symbol will be the keyword or your own identifiers. So actually, your compiler first is to look at, say, this is your program, and see if this is a legal program. Because the compiler will say, well, how do I know that this parenthesis is matching with this parenthesis? You must have matching parentheses, right? So your compiler is going to look over many things. So everything we do in programming also about language. So that's why we are going to learn languages in an abstract way. But in practice, in reality, a lot of things we do actually correspond to the idea of the membership of a language. Okay? Okay. So now we're going to extend this notion of concatenation, the length and reversal to languages in a simple way. So languages, right? So sigma. So this will be the example. So for example, sigma is AB, right? So this is a legitimate language. This is a legitimate language, right? So AB star, right? So this is sigma. So this is sigma. So AB star is a language. But then now, collection of strings, some strings is a language. So for example, this is a language. Actually, sigma itself is a language, right? So all these things are legitimate languages, right? So like I said, this is sigma star, right? And QZ is a language. The entire universe is a language. But this layer, sigma here, like this A and B, length 1, is a language. And of course, I could say, well, what about AA, BA, and so on. I just stop here, BB. I intentionally miss BA. This is a language, right? Well, this is finite. This is finite. Only 2 strings, A string and B string. This is infinite. This finite. Or we could have this, right? Say A, B, A, B, B, A, B, 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 A, B, 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 and so on. Now, the dot 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 is ellipsis. That means you know what I mean. Between you and me, you know that I have a pattern. So what is a pattern? The pattern is A's and B's. And I have so many A's and I have so many B's. So this is a language. A lot of time we borrow mathematical notation to say, yeah, what kind of, we can rewrite this as A and B, and n greater than equal to 1. Now, of course, I could say, well, what if I write something like n greater than equal to 0, right? So actually, this language is A0, B0, and then AB, right? A1, B1, A, B, B. So I have this sort of representation that this abbreviation if I have a string, say x to the power n, if n equal to 0, I want to say x0 is representing the empty string. Otherwise, if n is at least 1, then I'm going to say x to the power n is not really the usual power in your calculator. This is x you repeat this n minus 1 time, you concatenate itself, and then followed by the last copy. So this is sort of a very universal abbreviation, like powering, but it's not really the power in our usual sense. It's just a concatenation power. So you can see that we can have this kind of infinite languages. So in the form of A, M, B, N, and you repeat, if you have so many A, you have so many B's here. Okay, so it is a language. This is this with 0 here. Actually, this string is A0, B0. A0 is empty. B0 is empty. So actually, this language is this. Right? So this is this guy. This is this, right? And this is this. All these are languages over sigma. You will learn these languages later. So even with the doubleton sigma, we have different kind of languages. Some are finite. Some are just like this, we call it balance. Think about this. You write a C program or a contemporary program using contemporary programming language. If you use open parentheses, you have closed parentheses. You have the balance structures of the parentheses. If you throw away all the keywords, so you must have this. You must have this. Well, maybe you have this. Maybe you have this. Maybe you have this. Maybe you have this, right? So think about this. Before your program is understood, the compiler has to know, is this, what if you have an extra thing here? You mistype, you have these extra things. How does a compiler recognize this? And so somehow the compiler has to have one function that checks if the string looks like this. One simple form of the string, not like this, is like when I say this, right? Balance, balance, balance. This is the left parenthesis. This is the right parenthesis. So actually, the alphabet you have is this. Right, left and right. And the language you have in mind. So the language inside Sigma Star, the language you have in mind is this. Okay? So the collection of string you have in mind is no parentheses. Right? Because this is this and this. So actually this is empty. You can have this and this. So that means it is this. You have this and this. That means you have this and this. So in other words, you have a language that looks like this. And the compiler has a function that will say, yes, I like all these inputs here. Every string in this language is likable. Can you write a function that like this language, that choose this language, that say yes on all these members, right? So that is the deal. So your compiler would have to have a function that will identify this kind of structures. And of course, not just this. Your compiler will be able to do something like this. Right? Think about this. Can you write a function like this? Can you write a function that recognizes structure like this? Okay? In fact, it will be a good test of your representation. Like, you learn first order logic now. How do you tell someone to say, yeah, my program or my parenthesis structure look like this? What do you say? What will be the structure? You may say it's well formed. Well, actually, this is cheating. What do we mean by well-formed? Right? It's balanced. What do you mean by balance? The computer doesn't understand balance. The computer doesn't understand WELL-FORMED. The computer can only understand quantitative things. So actually, if you want to program your function to recognize a string like this, you better be very precise and let the computer know that your intention mathematically. So first layer is, can you use all the logical things that we learned to express strings in this form? Think about this. Now this one may be easy. This one is not that easy. Probably most of you sit down and come up with this. Okay? But you can try. You can try it tomorrow and see if you can give me the answer on this. Can you describe string like this? All of you who write program know that your program must look like this, right? But can you describe to your younger brother to say, yes, you want to write a balanced program? It must look like this. But how are you going to tell your kids? Oh, you know what I mean. Your kid doesn't know, because it has to have a rigid. You cannot say, yeah, keep on writing like this, then you know what I mean, right? No, we have to have a way to convey this to the computer system so that this can be checked. So languages would be sort of the properties of a function, and we want to study the properties of the language so that we know what this program or certain model is doing or computing. So now let's look at the operation on languages. Right? So first, we try to make it in parallel to the operation on string. First is the size or the order of languages. So again, we use this absolute value. This time, we want to say this is the order, this is the size of the language. So the domain of this is a power set of sigma star. In discrete math, or in some of your math courses, you learn the power set, right? I assume. So if I have a set A, the power set of A, so sometimes we use this script P of A, or sometimes it's 2 to the power A. That means this power set is the set of all subsets of A, right? So with that symbol, the power set of sigma star is to denote the set of all possible languages, right? So this guy here is the set of all subsets of sigma star, right? But subset of sigma star here is all languages over sigma, right? So that is our domain. And it's going to kick back natural number because it's to count the number of strings. So basically this order, the size is so-called the number of different elements of L, right? So let's say this F is language L. So for all languages L over sigma, this guy here is the number of different elements of L. So you use this in your course, is the order, the size, the cardinality of the set A. In this case, is the language L. So is you look at the language and then count the number of elements. Sometimes it's finite. Most of the times it's infinite like this, right? It's finite like this, so the number will be 3, a number will be 2, a number will be 0, this will be infinite, and this number will be infinite. So you count the number. The second operation is concatenation. So again, we overload ourselves. We're going to use this circle again. So we take two languages and concatenate the two languages. So first language, second language, and we take back the codomain is a language. So how do we define the concatenation of two languages? So for all L1, L2, which are languages, right? This one and this one. So how do we define L1 circle L2? Right? What is the definition? Basically, we consider all the possibility. You take a string from L1, you take a string from L2, and you look at all this possibility of strings from L1 and L2, and you concatenate them together and collect them together. So this, it looks like this. So this is x1 concatenated with x2. And you run this x1 and x2 arbitrarily in L1, and x2 is in L2, right? Not just one. All here, all here. So this is your L1 circle L2. Okay? All right, so let's look at some example. Okay. All right. So this one, say sigma is AB. So for example, this is AB, BA. Concatenate with say AB. So this is my L1 and this is my L2. Both are finite, so it's easy. Because when it's finite, we can just look at the combination and then do all the possibility. So the outcome is collection of strings. We take this is my x1 and this is x2, x1, x2, x1, x2, x1, x2, right? So it's like AB followed by A, right? AB followed by B, and then BA followed by A, BA followed by B, and that's it. And we have 4 different strings, and we list them out. Pretty straightforward, right? What about this? Like, if we have A and Bn, n greater than equal to 0, and concatenate with, say, the singleton A. One is infinite, one is finite. So this case is both are infinite. This case is, this is infinite, this is finite. The second one is finite. But let's see, what this means is that this is A0, B0, right? This is A1, B1, this is A squared, B squared, and so on. This is this guy. And concatenate with A. So the same definition, take all possibility from this, take all possibility from this, and concatenate. Well, there are lots of possibilities here. There's only one such possibility here. So we do this as A0, B0 followed by A, A1, B1 followed by A, A2, B2 followed by A, and so on. And of course, we can kind of write this out. This is A0, B0, which is empty. So this is actually A, if you really express this. This is A1, B1, A. So A1, B1 is A itself, B itself, so A, B, A, right? A squared, B squared is AA, BB, A. So AA, BB, A, right? And so on. So AAA, BBB, and then A, and so on. So this is the outcome. And of course, you may say, well, this is really clumsy. I start with a very compact notation here, and I concatenate this. And then you give me something that is clumsy looking. Sure, but this is a correct answer. Or you can spot that this is actually, you can rewrite this something similar to this, right? So actually, you can say, yes, I spot this. This is same as A and B and A, and then n greater than equal to 0, right? So certainly you can say, if I expand this, this is equal to this. So I know this is true. Or you may say, look, a typical string here is A and B n, typically. So A and B n concatenate with A is going to be A and B n A, just like this. And you run the n from 0, 0, 1, 2, 3, 4, 5, all the way up. So that's why you get this, okay? So one way or the other, you can have this concatenate language. Okay, couple more. So another one. So what if I have, say, A n, B n greater than or equal to 0? This time, concatenate to itself. A n, B n greater than or equal to 0. Okay. So what is that? What do you think? So I have A and B n greater than or equal to 0 as a language concatenate with itself. So we have the definition in front of us. We can use the definition, right? So you can expand this. Well, what is this language? This language is A0, B0, A1, B1, A2, B2, right, and so on. We can make it longer, right? A, B, B, and so on. This one is A0, B0. This is A1, B1, A squared, B squared, and so on, right? And then now the concatenation is that take arbitrary string here, take arbitrary string here, and then put them together. So arbitrary string here is this play, I can this one, and this one, this one, this one, this one. So you will see that it's a lot of them. So if I choose this one, so it's going to be A0, B0, and then mate with this, right? And then A0, B0 mated with this, and A0, B0 mated with this, and so on. That's just the first batch. And then what about this one? Right? So this will be A1, B1 mated with this, A0, B0, A1, B1, A1, B1, A1, B1, A2, B2, and so on, right? And then this one, right, and so on. So you know there will be lots of them. But do you see a pattern? Instead of writing this so long, so do you have a compact notation? And the answer is yes, we do have a compact notation. Actually, this you see the understanding is that the typical string in this set, it's always like A's and B's, and A's and B's. But the first segment of A's and the second segment of, say, this second segment, the first batch of B's, they have to have equal numbers. And these segments of A's and these segments of B's also have equal numbers. But these equal numbers and these equal numbers, they don't have to be the same. But these two numbers, these two segments must be the same, these two segments must be the same. So you understand that. So this collection here, you could say, yes, I know, I can write this as AI, BI, and then AJ, BJ. And then I is greater than or equal to 0, and j independently is greater than or equal to 0. So that is the deal. Right? Okay? So you can see the listing, and from the listing you ask yourself, what would be the appropriate exponentiation here to describe this pattern? Now, the reason why I introduced this is that if you say, well, a typical string is A and B n. A typical string is A and B n. So if we put them together, you will say, isn't it true that it's a and b n, and then a and b n, and then n greater than equal to 0, and then you collect them? And sorry, this is totally wrong. Because in integration, in summation, in everything you do in mathematics, this n here, or programming, is local. This n is this n here is local to this quantifier. This n here is local to this quantifier. This n and this n have independent scopes. So this n and this n will be no relevant relation. So you cannot assume that this n has a carryover effect to be this same n. So don't make that rookie mistakes. So to be safe, understand that, and you will see that you have this n here. You run the n from 0 to something, and you run the n from 0 to something. But in the process, you pick up an I here and mate it with this j here, right? So don't think that this, I can rewrite this. In fact, I can write this like this, right? It is the same thing. But sometimes you just say, what is L circle with L? So this is the concatenation. Okay, one tricky question, right? So hopefully you can see that the examples. Now, if I have language L, if I concatenate with this is a language. This is an arbitrary language, okay, over sigma. And you agree that, now if I write something like this, this will be nonsense. At the moment, it is nonsense. This is a language. This is a string. No such thing. We don't, at the moment, we don't mix a string concatenate with the language. But this is a language. This language has a single string. This single string is the empty string. So this is a legitimate language. So what is L concatenate with this special language called, with this singleton sigma? Sorry, epsilon. What do you think? What is the outcome? L. Exactly, this is it. You're right. L. So this is just like, again, just like 1. 4 times 1 is 4. 5 times 1 is 5. 1 times 6 is 6. This is like the identity with respect to this. Well, you can just expand this. This is a set of all x and y, right? X is in L, right, running over this. And y is in the second language, right? This is a definition, nothing fancy. Just write down the definition. Then you also say, well, how many choices I have here? You run the y in this singleton sig epsilon. What could be the y? The only choice is y is equal to epsilon, right? There's only one such choice. So in other words, you're looking at the concatenation with x, and you run the x arbitrarily in L. However, y must be chosen as epsilon. So actually, this guy is x epsilon. And you run the x in L arbitrarily. And this x epsilon, we know that somewhere earlier, we said that x concatenated with epsilon is x. So actually, this set is the set of all x. You run the x in L, right? Because you only have one choice. You have no choice but saying that y must be epsilon. So actually, this is same as L, right? You collect all the x, arbitrary x in L. So you're collecting L, all right? So that is equal to L. Now, obviously, you may sense the next question. What would be this? Right? What is that? L circle with the empty language. This is a language. This is the empty language, which is a legitimate language. So what is L circle empty language? Anyone? So I'm going to randomly pick and see if you can. You have any answer or guess? L. No, not that. You? Huh? Sorry? Any, sorry? Yes? Nothing. You mean nothing like this? Right answer. I don't know if there's a joke flowing around the internet for a long time. It's a very famous joke. They says that they have this survey questions asking the university students in the United States or in the world. The question is like this: tell me what X is, such that. So you say, okay, what is X if right? So this description is that I think Bill Gates wants X, something like this. Bill Gates wants X. Okay, and poor people have X, and so on. So if you look at this list, somehow they contradict to each other. But the question is, what is X? So turn out the joke was that they surveyed this question at MIT. Only like maybe 20% of the students at MIT would correctly answer the X. But if they survey this question at ABC University, assuming that ABC University is a very, very bad university, then most students will get this answer 97% correct. So actually, the correct answer to this question is nothing. X is nothing. So it's just like if somebody asks you, what is that? Then you kind of map to say nothing. No, nothing is the answer. So you think about this, right? Bill Gates wants nothing. Bill Gates is so rich. What else does he want? Nothing. But poor people has it. Poor people being poor has nothing. Right? So turn out, if you kind of map, you don't want to guess, you just say nothing. Turn out you get the right answer. So that was the joke. Okay, so back to here. It is really true that it is nothing. So actually, why it is nothing? It's very, you can go through the definition, right? So this is a set of all X circle Y, concatenated with Y, and you run the X in L, and Y is in empty set. Now, for this example, you say you have one choice. But do you have a choice Y in empty language? Then this time you say nothing, no choice at all. In other words, this will never be satisfied. This is always a contradiction, right? This is always false. No way you can find an element Y in an empty set. If this is a contradiction, then nothing matters here. This is a conjunction, right? So that means there's no way that this is satisfied. So this condition is actually always a contradiction, always false. So in other words, I don't really care how beautiful you write here. The y here will never make anything satisfied. So it is nothing. So it is nothing. So it turns out you're right. If you just say nothing, then you get the correct answer for some reason. Okay. All right. So there's another joke. I think it was funny. I don't know if you know about this few people in the history of the United States. We have Steve Jobs, right? Steve Jobs. And then we have Bob Hope. You know Bob Hope? Bob Hope was a famous comedian. He was a very good comedian. So, and then he always tells jokes in front of people, but he passed away many years ago. And then we have a singer called Johnny Cash. And Johnny Cash was a famous country music singer. So Johnny Cash also passed away. So the joke was that after Steve Jobs passed away, then people would say, now in the United States, there's no cash, and there's no hope, and there's no jobs. So because Johnny Cash passed away, so there's no cash, and there's no hope because Bob Hope passed away. And now Steve Jobs is gone, so there's no job. So actually, that's pretty good joke is that there's no cash, no hope, no job. So nothing left in the United States. So okay. So now we have some understandings of this concatenation. The challenge of concatenation is not just to study, say L1 and L2, and then say this is x1 circle x2, this is x1 in L1, and x2 is in L2. We can syntactically just say this, and do all the concatenation. The challenge is that something gets cancelled out. Okay, something somehow logically that become identified, and we do not know when this is happening, and that's why we do not know the outcome. So let me give you an example. Say, for example, you have this, say, for example, A, and this is A, just say A, for example. You have this is my L1, and this is my L2. Okay, so now both are finite. Seems it's very easy to deal with. Okay, but it emphasizes the points I want to make. If you're going to do this concatenation, you will see that A followed with this. So this is A, and this A followed by this, so it's A, and this A is followed by this, so it's A. So this A followed by this is A, right? And this A followed by this is A. So this A followed by this is A. Okay, so we have this. Now, you can write a program to do this, but somehow in this listing, in the outcome, some of them turn out to be repeated, right? So for example, do we have repetition? No, we don't, right? 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3. So somehow we don't. 1, 2, 3, 4, 5. No, I don't have repetition. But sometimes, so this example is a bad example. But sometimes this string, for example, this string, and this string, for example, somehow when you concatenate them together, and you look at all this possibility, this turn out to be equal. So in other words, the challenge is that sometimes we don't really get the entire universe. This is not true. it's not always you multiply the possibility. Some of the possibility become identified. They collapse. But we do not know who will be collapsing with each other, some others. So turn out, the challenge is that, well, can you describe the outcome? Can you know that sort of ahead of time, ahead of expanding all of them? Sometimes we are not able to list all the possibilities. Can you tell that who and who merge together, become one, become the same? Right? So that is a challenge. It's not like, keep on expanding, keep on enumerating. But sometimes we have to know some of them become identical and what they are. What are they? Right? Okay, so this will be concatenation. Then actually I thought that I was going to start the automaton. So it turned out the beginning of the automaton would be tomorrow. So let me continue with this more operator. That's the third one. Order and then concatenation. The next one is reversal. Right? So again, we overload ourselves. We use this little r or capital R superscripts. And then you give me a language, and I'm going to give you back a language. Okay? So for all L, which is a language, so what is L reversal? Really straightforward and intuitive. Just look at all the possibilities in L and reverse that, right? So this is a set of all X reversal, and you run the X in L. So every single one, you reverse, okay? So that is the definition, okay? The next things or remarks I want to make is certainly there are properties similar to the properties of all these operators together. So I'm going to just list some of them, right? So for example, for all languages, L1, L2, and L3, and so on, right? So we mentioned that, say, L1 circle this is equal to L1. L1 circle this is going to be empty, and L1 circle L2 and concatenate with this is associative. L1 circle L2 circle L3, right? And so on. You can make up a lot of possible properties and then prove that or disprove that yourself. Okay, but these are true. Of course, you can have like reversal. So you could say, okay, for all languages, L1, L2, and L3, right? And then you can say, well, what about this? L1 circle L2, and then reversal. Well, turn out, you will say you will see that this is L2 reversal, circle L1 reversal, L1 reversal, right? And again, you can come up with other properties that relate the operators together. But this one is pretty natural. Okay. And also, on top of everything that we have done, we have so-called language operators, right? So we have concatenation, we have reversal, and we have cardinality. So far we introduced this. However, when you go all the way back to your discrete math, you have self-theoretic operation, right? So you could have intersection, you could have union, and you could have set difference. So Now, because languages are simply subset of sigma star. So if you have L1, L2, you could talk about this. 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 All these things would make sense, right? Because you learn this from the usual set theoretic sort of notation. So what is L1 intersect L2? This is a language such that X in sigma star, say X is in L1 and X is in L2, right? So this guy, L1 union L2 is a set of all X in sigma star, and X is in L1, or X is in L2. This is a little bit tricky. Have you used this in discrete math? L1 minus L2. You have two sets. You take the set theoretic difference, L1 minus L2. Have you learned this? Remember? You have seen this? So, this is a set of all X in sigma star. X is in L1, but is N. X is not in L2. So the Venn diagram is this. This is a universe sigma star. This is L1. This is L2. L1 minus L2 is you want the string in L1, but at the same time you don't want that in L2. So that means you are looking at this part here. So this part here is L1 minus L2. This part. And of course you can say this part is L2 minus L1. This part is L1 intersect L2. Right? So you have kind of reached sort of rules. Is you can compose languages through set theoretic operation. You can compose languages use language operators, concatenation, reversal, and so on. So now this is a special case. This is the complementation. L1 complementation. Basically is sigma star minus L1. Right, this is a special case. The first operand in the set difference is the universe. Okay? So in your homework, maybe I put it there, is that, for example, you may ask question for all L1, L2, L3, languages, right? What about this? Is L1, say, L2 union L3? This is a concatenation, equal to L1 concatenate L2 union L1 concatenate L3, right? So, for example, is it true or not? If it is true, prove it. If not, disprove it. Okay? You can see a lot of properties that you can write out, and you can try and prove it or disprove it, right? Like this. Or if you replace this with intersection, is it true? If you replace this with set difference, is it set different? There are many interesting properties. Some of them true, some of them not true. Okay, so what the outcome is that you have some operators that come from the languages. You have the operators that come from the traditional sets. So now you can build more complex languages using operators from languages and the set theoretic operators. So you can make up a lot of these so-called properties and then try to prove it or disprove it. Now let me introduce some abbreviation. Okay. So the first abbreviation is so-called star. So sometimes it's called star, or sometimes it's called clean star. Clean was a logician with great contribution in language theory. So to honor him, this operator or this symbol is called clean star. Now, obviously, you may say, is it same as this sigma star? Well, turn out it is. But we generalize this. So what is L star? Basically, L star is this. It's an abbreviation for union of Li or Ln. N is greater than equal to 0. So what is L to the n? Exponentiation. So what is L of n? L of n is, we're going to define this inductively. If n is equal to 0, so what is L to the 0? The language raised to the 0. Well, you probably do not know what the good definition would be, but we're going to put it down later. But if n is greater than equal to 1, well, what would be the L concatenate itself n times? Our goal is to say it looks like this. Right? This is n times. So, as usual, we're going to isolate this. So that means it's going to be this Ln minus 1. Whatever this gives us, then the last time is going to concatenate L one more time. Okay? So this is concatenate L itself n minus 1 time. So remember, even L concatenate with L, it could be a lot of combination. A lot of combination. So with another combination, there will be lots and lots of combination. Okay? So you do this. But what if L0? L0 meaning that you don't concatenate to anything. Of course, you may say, okay, since this is a definition, I'm going to make this up. I'm going to say this is sigma. Okay, like I always say, this may be your definition, but this definition may be used by you only. So a good definition is to say, okay, what should be a good way to define L0? What should that be, right? So let's think about this. Consider L to the first. According to the recursion or induction, the program you write, it should be L1 minus 1 concatenated with L, right? This one. So now this is L0, concatenated with L. So in other words, in your definition, you want to say what would be a good definition of this, so that this definition concatenated with L would always equal to L to the first. L to the first, the semantics is actually, our natural semantics is that this guy should be L itself because it concatenates to itself one time. So what will be the definition here so that L is always equal to this definition concatenate with L. So turn out, you go back somewhere I erased, a good definition here is this. Okay, so that's why the definition, the natural definition is here. Okay, so L star is so-called the clean star closure of L. Is defined to be the union of all this concatenation, n-fold concatenation. So this is L0, union L to the first, union L squared, union L cubed, union all the way. This is a big set. This is a big language. This is at least an empty string. You know there's at least an empty string. This is L, and this is LL, and this is LLL, right? Okay, so you know that I did not write it down. Sometimes we get lazy. We throw away this little circle operator. So L1, L circle, L2. So this, we get rid of it. So abbreviation. Okay, so you see that L star is a very large language generally, and it is a closure. That means nothing escapes from this. You take any concatenation from this sigma, you are not going to get away. you are going to get back into L star. You take any string from L and you concatenate them together. So you are going to get it back in L star. So this is the notation. So sigma star is a special case. Sigma star, the special case, sigma 0, union sigma first, union sigma square, union dot dot dot. So this is empty. This is sigma. This is sigma square, and this is sigma cube, and so on. Right? So you can see that this is length 0, length 1, length 2, length 3, and so on. So the sigma star, you can say this is this guy, and this is sigma, right? So this is this, and this is sigma, and this is sigma square, and so on. So this is length is 0, this is length 1, this is length 2, and so on. So this is a twin star closure. Similarly, there's something called positive closure. Okay, it's L plus. L plus is almost like L star, but it is the union of Ln, the n-fold concatenation to itself. But this n is not from 0, it's from 1. Right? So actually this is n is from 1 to infinity, L to the n. So it could be L first, union L squared, union L cubed, union dot dot dot. Okay? So this one is L, this one is L circle L, so this is just like L. This one is L cubed, is L circle L circle L. So you can see that it has L inside, it has LL inside, it has LLL inside. And you connect all of them, then it becomes a positive closure. In some sense, that means you take some string from L and you do it at least once. So this is sort of like this. Conceptually, the thing is that this is the set of all strings from concatenating at least one strings of L. At least one string you take from L and you concatenate them. If you take 2, fine. You take 25, it's okay. But you take at least one from L and you concatenate this string and you put it in L plus. This semantics here, L star is the set of all strings from concatenating at least some strings of sigma star. This sum here could be 0. Okay, 0 or more. This one is 1 or more. Okay? So when it's 0, you take this, you take this, you take nothing. So you always have epsilon inside your L star. You may have epsilon in L plus. Because maybe if you start with L, L has already included the epsilon. So automatically you are going to have this built in. So epsilon will be always there. However, even you may not have epsilon in L here, but the definition will call for the inclusion of the L0. And L0, by our definition, is a singleton set with the empty string. So empty string will be automatically included no matter what. So if you look at L star, it has everything, including the empty string. So any string must be at 0 or more strings from L and concatenate together. This L plus is at least one string from L concatenated together. So this will be the introductory material for languages. As I said, Later on, whenever we deal with automata, we deal with regular expressions, we deal with push-down automata, we deal with context-free grammar. Sort of the language that we speak about will be always like strings. Languages, strain, strain, strain. Languages, concatenation, reversal, clean start closure. Our languages will be consumed on all this notation, all these language operators, okay? And of course, we mix with first order logic. You will see that we're using like OR, and we are using the quantified statement, all and exists and all. So this is sort of the starting point. Tomorrow, we will look at deterministic machine, and we will also look at non-deterministic machine. So we should be able to finish DFAs, and then we will start NFAs maybe the third hour tomorrow. Okay, sorry about the overtime. So I'll see you. I will release the first homework sometime today. Maybe after 5 o'clock when I get back to the hotel, because I cannot get onto internet. So once I get back to the hotel, I get on the internet, then I'll release homework number 1. Okay, all right.
They have opened about 2190.
They have opened.
They have opened it. Yeah.
Let me see.